1, and this is discrete probabilities. Let's see, let's go this one. Try something a little different this time. And I'm going to start off by saying that this is nothing new. However, the new part is the vocabulary, or how they're referring to things. So we're going to kind of go over that of, what they're calling. We call this thing a random variable, because we're now tying in probability with what we did earlier when we were doing frequency tables and relative frequencies. If you think of it in that way, this is really just relative frequencies being morphed into probabilities. So there's more of a conceptual shift, but the techniques for getting the answers and solving things are no different. Okay. There we go. So we're going to talk about something called a random variable. This is nothing new. It's just a name that we give to something that involves some randomness. And so we could think of the dice, rolling a dice, you get a 1, 2, 3, 4, 5, or 6. All we're going to do is call those outcomes. Instead of saying what's the probability of rolling a 3, we'll call it the random variable x. What is the probability that x equals 3? So you see, it's really the same thing, but with just sort of a little bit of abstraction to it. So a random variable, it represents a numerical value associated with each outcome. So notice this dice with one. Sorry about that. Get to turn that off. Notice this is really just a dice with a 1 dot on it. It's not a 1, but we're going to assign it the value of 1. And this one, because it has 2 dots on it, we're going to assign it the value of 2. Okay, so you look at it, well, it's got 2 dots on it. It's already a 2, but we're just making it more formalized. Okay, so this becomes the random variable x. When this shows up, it's x equals 1. This is x equals 2, x equals 3, x equals 4, x equals 5, and x equals 6. Now by x, there they are down there. Okay, so that's all a random variable is. But I remember the first time I learned this, I thought random variable, that's a weird name. It must be something really out there, something new. It's not. It's not. It's just we're calling it, instead of 1, 2, 3, 4, 5, 6, x equals 1, x equals 2, x equals 3. Okay. We can make x stand for anything. So we could do it rolling a dice, the number of sales calls a person makes in a day. And again, to be a successful phone salesperson, you got to make a lot of calls. But that could be the random variable. How much time you have, how many calls did you make? Could be the hours spent on a sales call in one day. So notice that's the important part. What are we going to call x? Is it the number of calls, or is it the number of hours spent calling? It could be two different things. Okay, so payroll might be more interested in how many hours someone spends if you're getting paid hourly, but if you're working on commission, you might get paid by how many calls you make, or you just might, so we can set it up any way we want to go about doing that. Okay, to get back to this, we talked about discrete. Does anyone remember what the other type of variable was if it's not discrete? Continuous. Good. So these are kind of the things. I hate when that happens, right? That's okay. So a discrete variable is something that happens. It's a particular value, like 1, 2, 3, 4, 5. We talked about shoe size. You can have a half, like there's a 10, 10 and a half. 10 and a half is my preferred, but sometimes I like 11s because they give a little bit room. But there is no 10.75. I think that would probably be the perfect fitting shoe for me, but there's not one. There's a 10 and a half or 11. So I got to figure out which one. One's a little tight, one's a little too big, but hey, that's what I'm stuck with because the shoe sizes are pretty much discrete. Although when I go to Thailand, the European sizes, they do by, I think, millimeters. So it's 43, 45, 43, 44, 45. So those actually fit me a little bit better than the American sizing of shoes. Anyway, discrete, right? you can't get the stuff in between. So it's just dots on the line. So number of sales calls would be 1, 2, 3, 4, 5, or maybe 0. You just didn't want to get started. I used to have to do that when I was working in the insurance office. I didn't like making calls. Somebody else do this. So got my boss to hire somebody to do that so I could focus on the other stuff. A continuous random variable might be those hours, right? Because you could spend 1 or 2 hours or 3 hours, but you could also do a lot of partials. And I remember this when I was on the time card. I used to work in restaurants and stuff. You clock in and out. They always rounded it to like the nearest 15 minutes. Actually, so if you clocked out with 14 minutes, you actually got rounded down. You had to, and that's why we'd stand around the clock and wait for it to click to that next stick. So we got our full 15 minutes on there. So they didn't like when we did that. But if we did it continuously, we could just punch out and they would pay us for 14 minutes or 10 minutes or whatever. So that's what the idea of a continuous is. You can have all those hours and you can have anything in between. Okay, so that's the idea of a continuous. I want to remind you, we're going to go back to this one. The slide is just, we've seen this before. Remember, discrete is 1, 2, 3, 4, 5, and continuous is any value in between. And what I use as a musical example, the fretted guitar is discrete. You can just play the frets. You can tweak it a little bit if you play right on the fret, but not much. Yet a fretless guitar, you've got a lot of freedom in the notes, which for some of us is not a good thing because it's harder to play a good song. But really good musicians, fretless guitars and stuff, they do wonderful with it. Okay, that's continuous versus discrete. Okay, what we're going to focus on for the next 2 sessions. So we're going to do today, we'll probably be finishing up maybe in 10 or 15 minutes. We'll take a work break and then we'll pick up at 10 o'clock. So I'm going to do this because we have 2 lessons each day, give you a time to kind of get into working on the homework, and then we'll come back and do the second lecture. Okay. Remember, they're already pre-recorded, but I may be doing a little bit different each time. But if you needed to take off or whatever, just remember everything is recorded from spring, so you can always get ahead. In fact, I've got a couple of my classes, they're already through chapter 6. How'd you do it? Oh, we just watched the videos. Okay, cool. So you can do that too, and especially if you miss. So these are just examples. If we let the random variable X represent the number of Fortune 500 companies that lost money in the previous year, is that going to be discrete or is that going to be continuous? 500 companies, the number that lost money. Discrete? Discrete. Why? Because you can't have 1.5 companies that lost money. You either lose it or you don't, right? And we're going to see that's also called a binomial experiment. That's our second part of today. It's a special type of random variable. But yes, that is discrete. There's 5, 6, whatever, but there's a specific number. There's not 1.5 or 1.25 companies. Oh, they lost some money, but they gained. No, you either lose it or you don't, right? You either lose, break even, or you make some money. How about if we let X represent the volume of gasoline in a 21-gallon tank or in your car? Is that going to be continuous or discrete? Think about your gas gauge. How does it work? Is it digital? Or is it just, it's going to show you all the way along the way, right? It's continuous. So those gas gauges are continuous. So you could be down to 3 gallons, or you could be down to 2.9 gallons or 2.99, anything in between. So the gasoline comes down, it's continuous as it's being used. Okay, so that's just a concept. And again, for at least the next 2 lessons, we're going to focus on discrete variables. We will get into continuous a little bit later, and all our tools will work similarly for the most part. Okay, so a discrete probability lists the possible values of each random variable. So it could be 1, 2, 3, 4, 5. Sometimes it could be 1, 1.5, 2. So we just follow through with that. But when we called it a discrete probability distribution, so this is where we kind of make the crossover. So we were looking just at data, but now we're looking at data as probabilities. There's a couple conditions. Thinking about probabilities that we just talked about, can you think of what are some conditions that probabilities must follow? Right? Probability is a decimal. It's a fraction. Yes, sir. Excellent. Right? Because you can't have more than 100%. You can't have less than it. You have to count everything 100%. One. Perfect. That's one of the rules. And so all of them together have to total to 100%. What about each individual probability? What are the parameters for an individual probability? Could it be negative? Negative probabilities? No, we haven't done those, right? So what's the lowest probability it could be? 0. Means impossible. What's the biggest it could be? 1. So it has to be somewhere between 0 and 1. And again, if it's 1, then that means there's only one thing that can happen, and it's certain, right? So they all have to add to 1, or 100%, and each individually has to be somewhere between 0 and 1, or 0 and 100%. That's the only two rules that we really need, okay? So they show them here. Again, when you add the probabilities, and again, with random variables, we use P of X, or the probability of X. And again, remember that random variable is just going to be a number of how many times it happened, okay? Especially with discrete, that's what we'll start with. So the sums have to be to 1 or 100%, and each individual one has to be in that range of 0 to 1. Okay. So a couple things is, how do we construct a probability distribution? Again, it's a new vocabulary word, a discrete probability distribution. And I'm going to tell you again, we've actually already done this. When we made relative frequency tables, that's exactly what we were doing. We just didn't call it a probability then, but now we're throwing in probability. So if we start off with a frequency table, this was for a passive aggressive test traits. It was given to 150 employees, and each individual was scored on a scale of 1 to 5, where 1 is extremely passive, 5 is extremely aggressive. A score of 3 was sort of in between. The results are shown. Construct a probability distribution for the random variable X. What's a probability distribution? It is a relative frequency column. So all we need to do for this is, since we have 150, actually you could, if you wanted to, you could see these are going to add to 150 because they're all here, but they also total us up here, so we kind of skip that step. Take their word for it, there's really 150. And so how do we get the relative frequency for each of these? What do we do mathematically to get relative frequency? We take the frequency, and we take the total. Do we add, subtract, multiply, or divide? Divide. So yeah, the opposite of multiplication. So once we have it, we take that relative frequency, and then we can multiply it by the number, and we get the number that it happened, right? So 24 divided by 150 is going to give us a relative frequency. Remember, this is also going to be a probability, so it's a number between 0 and 1. Okay, so it's a, and I won't do it with each because the next table is going to give us all the answers, but I would just go through and divide each of these by 150, which is the total. And I don't think you're going to do this much because it's most of it is already going to be set up for us. And what you'll see is, by doing this, since we're dividing by the total, this total becomes 150. They will all sum up to 1. So the total, once we get them, they'll become 1. So I think I'm just going to go to the next chart. So this is if we actually did the calculations. This is 24 divided by 150, would round it to 0.16. So we've got each of these, and we see that this becomes a probability distribution. It always will be, because we're dividing by the total. The total is whatever, the same. So it's always got to add to 1. And each individual probability, each individual relative frequency is always a decimal somewhere between 0 and 1. And we see that that fits the definition. So whenever we take a frequency chart and it counts everything, and we make a relative frequency, we are always also making a probability distribution. And I think I mentioned it earlier that once we get these relative frequencies, we can think of it that 3 is happening 28% of the time. So if we just throw some randomness in, we're going to randomly choose something, that's when it becomes a probability. If it's not randomized, it's not a probability. It's just saying 28% of the people scored a 3. So that's not really a probability. But if we're going to randomly select somebody, that becomes a probability for the chance of getting someone who did score a 3. Okay, 28% chance of getting somebody who scored a 4. If we're randomly picking people out, is a 20%, because there's 20% of them scored a 4. So it just depends on how we're talking about it. Okay, questions? Okay, so now we're going to get into how we can use relative frequencies, probability distributions. Just remembering this isn't anything new. It's just taking a frequency chart, getting a relative frequency, and calling it a probability, because we're going to randomly choose someone from the group. Okay, that's the only difference that's happening now. Okay, these are all the steps. If you want to go through it, we just did it. Usually we'll start with a frequency distribution. We've got to have that somewhere. We've done that. Sum up all the frequency, or read up. It's told us we had 150 was the total summary. And then we got the probabilities by doing a relative frequency. So you could call it a probability, or just go back and it's really just a relative frequency. So that's what we did before. We're now calling it a probability. And you're guaranteed it's always going to be between 0 and 1 for each individual, and the sum will always be 1. Sometimes you might get a little bit of a rounding, so you might only end up with 99.99 because of some rounding in there, but effectively everything will be 100%. Okay. And we did this before, right? Once we have the relative frequency, we can make a, what do we call this? Histogram, right? Bar chart if you want. And it shows here visually all of these. And what we're going to see is the beauty of all this. Once we start with and we're going to do this for this particular example. Remember, this is a score of 1 to 5. 5 is aggressive, 1 is passive, and everything else is in between. The percent of the people who scored those things. Numworks is actually going to create this for us with bars. And we're going to be able to get each of these. Anyway, we'll be able to do a lot of things with this. Okay. So, again, nothing new, but now we're just using some different terminology. Okay. Here's another example. So if we weren't given the frequency table, but we were giving this chart with the relative frequencies, and we're asked to verify if this is a probability distribution. So we're looking for 2 things, and 2 things only. The homework has a few of these. You're looking that each of the individual probabilities are between what 2 numbers? 0 and 1. Okay, and they are, aren't they? They're all decimals, somewhere between 0 and 1. So that, check. Number 1. Okay, each individually, yep, that's good, that's good, that's good. Do they all add to 1? Well, we have to add them together. And again, we could do that, and we'll see in this case, they actually do all add to 1. So if we add them all up, total is 1. Each are in between there. So this is a probability distribution. Okay. So now the thing we need to know that is, so then now we can apply some of the other things. We can find the mean and standard deviation with some special formulas once we know this. Okay. We're going to look at another example. Is this a probability distribution? Well, we look the first step. This is between 0 and 1. That's between 0 and 1. So they're all between 0 and 1. That's good. But if you add these together, what you're going to see, let's see, 5, That's 8. That's 9. 9 and 8 are 17. So there's going to be a 7. Carry the 1. That's 2, 6, 8, 10. So we get 1.07 if you add them all together. Is that a probability distribution? No. Even with rounding errors, that's way too off. Now, maybe 1.01, I might say, okay, maybe there was, but no. So if it's the first, but the second, its sum is 107. So it's not a probability distribution, which means we can't use this for doing probability distribution stuff. It's something else. I don't know what it is. And again, there's things out there that have decimals and stuff, and these might be percentages, but there might be some overlaps. It's just not a probability distribution, okay? Because you can't have more than 100%. You can't have 107%. That's not probabilities. 100% is the biggest. So far, so good. So again, on the homework, there's a few in there. That's all you're asked to do is they'll say, is this a probability distribution? Are each individual ones between 0 and 1, and do they add to 1? If they don't add to 1, no, they're not probability distributions. Okay. So now is where we get the fun part. Again, this will go a lot quicker. There is a special formula for getting the mean of a probability distribution. So this is kind of getting at what happens on average. We're going to see that we give this another name. We also call it an expected value when we're doing probabilities. So a lot of times we apply this to like lotteries. What's the prize size? What's the chance of winning? And so what is the expected value? We do that when it's done a lot of times. Okay. So notice it's just the sum. What you're doing is you're taking each of the discrete variable values and multiplying them by their probability. We're going to see that we have a tool built into NumWorks that will do all of this for us. And we've actually already used it. It's just called a weighted mean. When we were doing a weighted mean, that's all we're doing here. So we could say this, for this is all we're doing is a weighted mean. And is weighted is I before E's or E before I apologize if I've got it wrong because I get so big. I usually can't get it right because even if I get it right, then I second guess myself and I get it wrong. But apologize. Okay. So this is the way I want you to do these questions. So they will give you a probability distribution. And as long as it's a probability distribution, the mean is you take the X, and we'll do this by hand afterwards. But what I'm going to do is I'm going to show you, we can go to the NumWorks calculator. And if you click on this, I did actually already put the values in to save us a little bit of time. So that's the first thing you do is you'll come to the calculator tool. You'll go to statistics, right? We did this before. You'll enter your values and you'll enter the frequencies, which are probabilities now because we're randomly choosing someone out. That's all you have to do. So you do that part. And then what do? We come over here, we go to stats, and here are our answers. What we're looking for is the mean, and let me go to full screen so it's easier to see. And actually, let me go back. So data, you see the data's been entered in. I'll hit this and we'll go over to the stats. You could even go to the graph. The graph will show a histogram if you want. So see, this does it all for us. That's kind of cool. Don't need it right now, but it'll do it. Stats, and then what we're looking for is the mean. There it is, population mean is 2.94. Maybe write that down because I'm going to, next slides, we'll see how to calculate it, and the hand calculations also come at 2.94. But what I'm going to do right now is I'm going to show you, before I even show you the formulas and stuff, how to get the standard deviation and the variance. Actually, the variance and the standard deviation. Notice we just plop down here. Our population standard deviation is 1.27. If we rounded it to one decimal place, it'd be 1.3. You're going to see that in a slide after a bunch of calculations. And the population variance, 1.6164. You're going to see that exact value done with hand calculations. Again, would probably take about 10 minutes, but the longest part of this was to enter the values, which was still less than a minute. Okay, so once you go to NumWorks, enter it in, and you just come over here. This is how you're going to get all your answers for probably the first 10 to 12 questions in the Chapter 5 homework. Okay, so now I'm going to go back here. And again, if you pull up the slideshow, you can click here and it's got it entered in for you already. So we're going to keep, so the way we would do this by hand is you're going to take each of these x values times each probability. It's got that. So that's that. And then you're going to sum them. You're going to add all of these together, right? So 5 is 0.14 times 0.7. You add them together, 2.94. Isn't that what we had? Well, calculator's still there. 2.94. Calculator did it for us. It's just a weighted mean. Okay, but when you start doing this, in fact, actually, I didn't realize that until today because I was always taught this is called expected value and you have to do it this way. I got that's exactly what we were doing when we were doing weighted mean. This is nothing new. Okay, and that's what I want you to see is math. A lot of times we just give a new name to something we already did before. Weighted mean. Okay, but the cool part is the next step is remember standard deviation and variance. That was usually a gnarly calculation, right? We've already done it with the NumWorks, but I just want to show that it works. You could follow this formula. Remember, you're taking each x value, you're subtracting the mean, you're squaring it, and then you're multiplying it by the probability. And then you have to do all of that, add them all together, and then at the end to get the standard deviation, once you've got that value, you take its square root. Now notice this one we are not dividing because the probabilities all add to 1, so they act as, they give it the weight. So this is the process you would go through to do it by hand, but I'm going to show you, we've actually already done this with the calculator. So once you get sort of faith that the calculator is going to do all the calculations for you correctly, that's good. What I want you to focus on, what is the standard deviation? If this is the mean, what is the standard deviation? It's sort of how much we add or subtract from that mean to get the spread of the data. So I want you thinking of that, and and in the homework they'll ask you, what does this mean, right? So then we had to do this. We have to square each one, and we're not even done yet. We have to take the square of each one and multiply it by its probability of happening, and then we have to total it, and we get the 1.6164, which is what we got here as population variance. Okay, and then what do we do with the population variance? We take its square root, and we get 1.27, or round it to 1.3, which is also what we got from the calculator. Calculator did these processes for us. What I want you to do is just think, how would I get this? Well, I'm taking the mean, I'm getting variation from the mean, okay? And we will use these and just think, standard deviation is how far from the mean things are going, and it's adding and subtracting because the mean's always in the middle. And we're going to use those. So far, so good? Okay, so you can do it the long way if you want. Yeah. And maybe it's helpful if you want to do it once, just so you kind of understand. That's up to you. But if you kind of see it and you go, okay, I'm just going to do the calculator, and I'm telling myself, oh, the mean is about 3. It's 2.94, and then it's plus or minus 1.3. Okay. Most of the data differs from the mean by no more than 1.3. So that's a standard deviation. Okay. And we're going to see kind of from that empirical rule, we talk about being 1 standard deviation away, 2 standard deviations. Anything beyond 2 standard deviations is considered kind of extreme, not really likely. Anything within 2 standard deviations considered somewhat likely. Okay, so that's kind of what we get. And that's what we're doing with statistics. We're looking at, is what we've got, is it sort of usual or unusual? Okay. I have 2 cousins. They weren't growing very fast when they were kids. They let the boy go, and then his sister, she was also kind of small. So they took him. The doctor says, yeah, their growth rates were below, not only below average, but they did some genetic tests, and they found they had a form of dwarfism. My cousin, my male cousin, he was older by a couple years, so when they started doing some treatments, his was not as effective. He's still he's I think about 5 foot, um, but his father's like 6 foot. So his genetics probably would have had him being taller without that genetic. But the girl is a little over 5'2", so because she started getting treatments earlier. But that was all because of statistics, right? They said this is not usual. And if you're any of you parents yet, no, maybe. But when you that's one of the things you're going to want is this normal for my kid? They do this, they do that, um, and yeah, there's variation is normal, but there's outside of that. That's when we want to be concerned, and maybe there's something that we need to go to the doctor for and see if get some treatment because it's not normal. Okay, it's not. It's outside those. So expected value of a discrete random variable. Again, we just did this. It's a weighted mean. Maybe I need to delete that. Oh, let's do it one more time. So this is called expected value. And this will be our last slide. I'll be done here in 5 minutes, I think. And what we're going to see is we're going to create a probability distribution off of this. And that's the first thing we're going to do. And then we will be able to use our calculator for everything else. Okay. So finding the expected value, here's a raffle ticket. So like a lottery, they sell 1,500 tickets are sold, $2 each, and there are 4 prizes, 500, 250, 150, and $75. You buy one ticket, find the expected value, and interpret its meaning. Okay, so what we're going to do is set this up as a probability distribution. First of all, 1,500. Everybody walks. If you walk through the door and you buy a ticket, what have you just done? You've lost $2, haven't you? Or you've paid $2. It's usually for a good cause, so you're okay with that. But everybody loses $2. So even the winner who won 500, they didn't really win 500 because they lost $2 when they bought the ticket. So we're going to say that the X value of this prize, the X value of this prize, get my writing tool, is not 500, it's $498. Okay. The value of the next one is not 250, it's 248. So I'm subtracting 2 from each of these, right? And that's the cost of the ticket. 150 is going to be 148, and 75 is going to be, is that 73? Taking off $2. And if you lose, you've already lost your $2, so we'll do that as -2. Okay, so everyone in the lottery will get one of those prizes. And most of us will get the -$2 prize. We'll pay our $2. But again, it's for a good cause or something. That's why raffles are usually done. What is the probability of winning? Again, they're going to pull out a ticket and they'll do this in order. So if you win the 500, one ticket is called, right? So that is, what's the probability? 1 out of 1,000. Yeah, okay, good. Something 1,500. This ticket also, one ticket out of 1,500. And this 1 out of 1,500. And this out of 1,500. Again, that's at the beginning. That's your probabilities of winning. Notice once they start drawing, if we use conditional probabilities, that there's one less ticket. So actually, once they draw the first one, there's a little slightly different probability here, but it's so slightly different we don't need to worry about it. Okay, 1 over 1499 is so close to 1 over 1500, so we just calculate it this way. But if you're thinking, wait, this isn't conditional probabilities apply here, you're right. We should actually, but we weren't given the order that these would be drawn in. And the probability of losing, we'll kind of do that, is going to be, since there's 4 winning tickets, everybody else will lose. So what we do is 1,500 minus 4 is 1,496. out of 1,500. Okay. And again, to be exactly right, we would probably, anyway, that's how we do it. So this, just kind of thinking there'll be 1,496 losers, there'll be 4 winners, and these are the amounts they'll win. And then what we do is we use the multiplication rule to get the probabilities. We take each of these, multiply it times its probability. We'll get a total here. But that's not what I'm going to have you do. Once you have it set up, what you're going to want to do is say expected value is really just a weighted mean. So if you click on this one, again, I've already got it set up. It'll take us to a different one. I'm going to go full screen. So 498, 248, 148, 73. So those are the possible winning values, right? These are the probabilities, and I'm just going to show you that they're actual probabilities. Oops, come back here. That this number, which is hard to read, right, 6.666 e to the minus 4, you'd move that decimal place back 4 places, so it's 0.00067. It's a really small number. It really is just 1 divided by 1,500. That's what I put in there, but it turns it to scientific notation. And then this last one, what I put in here was 1,496 divided by 1,500. And I get this value. Okay, so I'm just putting the probabilities in there. And again, all I need to do now for expected value is I go to stats, I go to the mean. This is going to give us a weighted mean. So I arrow down, and the population mean is negative 1.35. So what does that mean? On average, everybody will lose $1.35. Okay. On the converse, what it means, so that's because remember there's 2 sides. There's the people who are buying the tickets. So on average, everyone's going to lose. What does that mean for the people who are selling the tickets? They're going to gain $1.35 for each ticket that's sold. So the organization we're working with, 1,500 times 1.35, that's how much money they'll make off of this. Even though they've got prizes they're paying out, it's coming out from this big pot of money that they made. So what it tells them is that this will work. This will raise some money. You've got to do this beforehand, because if you make your prizes too big, if your organization comes up with a negative expected value, that means you're going to lose money. Positive means you're going to win. And remember, there's always 2 sides to the table. If I'm paying out here, if I'm the customer going to the lottery house or whatever, that's how we calculated it, is from my point. If you calculate it from the point of view of the organization, then what happens is when we come back here to the data, these are payouts. So these would all be negative, and this would be positive. But look at the probability for them of a positive. It's pretty good. So again, so expected value always has a sign of either being positive or negative, and you have to interpret it by which side of the table are you on when you're doing the calculation. When we did this calculation, we're on the side of the table of the people buying the tickets. But if we were on the side of the table of the people selling the tickets, the negatives will be changed, and that means they're going to make $1.35 for each ticket sold. Of course, you have to sell them all. That's what it means if you sell all 1,500. If you don't sell them all and you get to the same prices, you might lose. But does that make sense? Expected value. But just when you see a question about expected value, maybe substitute the word weighted mean, and it'll make it easier. It's really just taking that distribution, that frequency, relative frequencies, getting a relative weighted mean, and that's what an expected value is. Okay. And you could do it by hand, which we sort of did, right? We had to do this calculation, subtracting the $2. You've always got to remember the entry fee. Everybody's losing at the very beginning. People who don't win a prize, they get 0 minus the 2, so that's why they get the minus 2. This is the table we set up, right? There's only There's 4 people who won, 1,496 who lost. So this would be what the calculation would look like if we wanted to do it by hand. And again, there's so much area for it would take longer, and probably for me, I might have to do it 2 or 3 times before I got it right. But if I enter it in the thing, minus $1.35, that was that weighted mean that we got. Okay. So we're going to lose an average of $1.35 per ticket. Now, nobody actually loses $1.35, right? You either lose $2 or you gain one of the prizes. But it's just kind of averaging out the results. Okay, so for the community response. And that's the last slide. Tell you what, I promise you next time will be faster, because now that we've got the theory behind it, we're going to take a look at something called a binomial, which is a special discrete probability. There's a special tool for calculating it, and I'm going to show you that after about let's take a 15-minute working break, bathroom break. So we'll come back at 10, and I'll try to make this schedule consistent from here on out. When we're doing 2 things, we'll start one at 9, we'll start the other at 10. And any time in between that's available for us, you can kind of work on homework or take a mental break, because it's a lot of information coming at you. Okay, so we'll break for now. We'll start up again at 10 with, what are we doing? Binomial distribution. Binomial. Okay.